Okay, guys, let's continue. All your midterms are graded, and if you have any questions about it, let me know. If you need any help, let me know. If your aggregate points are less than 50%, you should panic, and just ask me for help anytime you need it. Any questions about the midterm? All right. So let's see. How many people do we have? All right, enough. Your last time we started a simulation in OpenFOAM, and it should have finished like within an hour or so. Today we'll look at how to visualize all of that. Okay, there's one chat. Let me check. Chat says, do you know where the class average sits? Class average is, no, I don't remember, but it's like 60%, 70%. I don't know the exact number. Okay, so to figure out how to actually see what the simulation did, let's open our Ubuntu again and go to the place where you ran your simulation. Okay, working. Still working. Okay, perfect. All right. So where did we run it? Let me see. We ran it here. DTC wave. Okay. And if you look at this directory, you should have all of these directories called 0, 0.1, 0.2, etc. Okay. There's another chat, which is, when will we have the second quiz? We will have it like in within 2 weeks. Okay. Any other questions? Okay, all right, perfect. Okay, so everybody, let's go to the directory where you ran your simulation, and you should see these directories 0 through 1. That's basically because we said you should save every 0.1 seconds. So that's what it has done. And you should stop running at 1 second. So it stopped after 1. All right. And let's open Explorer here. Okay. So the thing is, ParaView is installed on our Windows partition, and there's no easy way to view what's happening on the Linux partition. So what we can do is we can copy this whole directory onto our, just let's say copy, and let's put it somewhere. I'll just put it in downloads. You can put it on your desktop. Oh boy, okay. So just copy it somewhere on your Windows partition. C drive, desktop, wherever you want.
Could you go back to what you typed in the Linux terminal?
To open the Explorer, explorer.exe. You need to put the dot, space dot here. Otherwise, it will just open a random Explorer window. Dot means here. Okay. So I haven't figured out a good way to tell ParaView where the Ubuntu stuff is. So this is my shortcut. But if you find a good way, let us know. All right, while it's copying, in the meantime, let's open ParaView. All right, he's done. So now we have this on our Windows drive. Next, to be able to open all of this in ParaView, we need to create one text file here an empty text file. So let's call it, let's open Notepad and just leave it empty and just save it as, you can give it any name, so any name, but the extension should be .foam. Okay, just change this to all files. All right, and we'll save it in the same directory, DTC hull wave. Okay. We don't need to put anything in this text file. It just has to, there has to be a text file with this name, with the extension .foam, that one. Now we can go to ParaView and say open. Go to wherever you saved it. So I saved it in downloads, DTC hull wave, any name.foam. Once you do that, you have to hit apply. Okay, and then you should see a block like this. So I'll wait until everybody's here. Any step that you need me to go over again, tell me. Is everybody here?
Still copying over files.
Oh, so
Yeah, still copying.
Okay, okay. So let me just hang around for like 2 minutes. Mac users, are you able to run simulations?
Yeah, I had mine running last class, but right now I have something going on with my Docker, so it's not working right now.
Wait, you said it was running, but right now what's happening?
I have to use like this program called Docker, and it's not opening for me right now, so I'm just trying to troubleshoot that right now.
Oh, okay, okay.
I'm going to catch up later.
All right, all right. Yeah, with the Mac, you might not have to do this copying over because you don't have this separate subsystem. Okay, anybody here yet?
I'm there.
All right. Anybody else? So ParaView works best when you have a mouse. With the trackpad, it's nearly useless. Wheel scroll is zoom in, zoom out. Hold wheel is pan left, up, down. And left click is just rotate. Okay, so just as a reminder, once your copying is done, create this empty text file called whatever.foam. Save it as .foam, not as .txt. Okay, let's see. Anybody still copying? All right, let me ask if you've been able to open ParaView here. Abigail, did this work fine for you?
No, I'm still having trouble with Docker, just like Daniel. I'm running on a Mac.
Oh, okay, okay. Yeah, I've never tried to run it on a Mac, so I don't know how to fix. Brendan? Brendan, are you at this point?
I was just gonna go back and do this later.
Oh, okay. Chad,
Yeah, for the most part.
so you're here? This is open for you?
Yeah.
Okay, perfect, perfect. Daniel, ratio?
I'm there.
No?
No, I am there.
Oh, you're
Still.
here. Okay, okay,
Yep.
perfect. Let's see who's next. Griffin.
Yeah, I'm there.
All right. Then Raymond.
I got a little bit of trouble, but I'm gonna catch up.
Meaning your simulation ran fine, but you were not able to copy it over?
Correct.
Were you able to open like the explorer.exe like we did here?
Yes, it's gonna take me a little bit more time, but I will be able to catch up. So
All right, because yeah, I mean, I really want all of you to follow along because there'll be many clicks and it becomes difficult later. So if I can help troubleshoot right now, you tell me. All right, Roman.
Yeah, I got it.
All right, Tobiah. All right, Tom.
I've been trying to catch up and I have everything working fine, except I didn't go and set the simulations to run. So I'm going to have to do that and then catch up. But I'm
Okay.
recording all
But-
this and then I'll, so forth and get caught up.
All right, so but all the setup works fine and you just have to run the simulation, correct?
Yeah, that's right. I'm getting all the directory stuff and the files and I just have to set the simulations to run.
Okay, okay. Declan, Paraview,
Yep, it's working fine.
John.
Just finished copying. I'm making the text file now.
All right, let me know if you have trouble opening in Paraview. Mario. Mario. Okay, Miranda. Okay, don't know. Zach.
I actually just had to get a new computer on Monday, so I'm still catching up downloading stuff.
Okay, all right. So seems like half of us are here at this point. And so I think we can go ahead. So Paraview is wonderful, beautiful. You can do many things with it. So you can change the background to black or white or whatever you want. And what this is showing is it's the grid block that we simulated. So if you want to see what's happening, there's all of these drop downs, okay? Go to this drop down that says P. P is pressure. And you see all of these different variables. So you can color your simulation using any of these variables. That's U is velocity. So that's the velocity in the field. Alpha water shows you the distinction between water is 1, that is red, and air is blue, that is 0. Okay. Then others we don't care about. There's one important one, PRGH. So this is the pressure, okay? This is the pressure without considering the depth, rho GH part. So PRGH is one of the important ones. Velocity is the other important one. And you'll notice that velocity is a vector, and what's being colored right now is the magnitude. That's the second drop menu here. We can just look at the x velocity, y velocity, or the z velocity. So let's look at x. Okay, and zoom in. Let's see. Okay, so we have large x velocity here, where we see the darker red. And this is the axis you should use to orient yourself. X, Y, Z is shown here in the left corner for me. All right. So the first thing we will do is, well, before we do anything, let's make this solid color and look at what has happened. So do solid color, and then come here to surface, make it a wireframe. All right. So you see this actually shows this simulation grid. So that's how you solve any numerical problem. Whether it would be finite element, you have to break up your solid into elements. With the fluid simulation, we break up our domain into these cells. And if we zoom in enough, we will see the silhouette of the hull here. Right? So that's our hull that's embedded in the grid. So basically that acts as a solid surface, and all the fluid flow goes around it. Okay, so everybody's able to see this? Any trouble? Just to superimpose the actual solid on top of this, we can go to, actually it won't be there. Let me check. Constant tri-surface. Yeah, it's not there. Okay. So the STL file that we were able to visualize earlier, we can open that in the same place as here. Let me see if I have the STL file. I should have it here. Yeah, perfect. So last week I was visualizing this DTC scale.stl. So let's just use that and put this in ParaView. So we just say open, go to that place. Where is it? It's in downloads, DTC scaled, apply. All right, and you see that that's our ship hull. And you can put any hull design you want, a catamaran or whatever you want. So anybody have any trouble with this up to this point? So we haven't visualized the flow yet, but we'll do that in 1 second. Everybody's comfortable navigating around ParaView? Anybody have any issues? Okay. So next, let's so you have to select. Remember, when we look at this browser here on the left, this window, it's showing our different things loaded into ParaView. So we have our DTC scaled solid object. If you click the eye, you can make it visible or invisible. And to make changes, you can even visualize this as a wireframe. So now it's become a mesh, and you can zoom in and look at this. Okay, so remember, computers don't work with solids or continuous things. Everything has to be a mesh, because everything has to be depicted as points. All right, there's one chat. Let me check. How did you get the hull to show up? Okay, so let me remove the hull. So I'll delete the hull. Okay, perfect. So now say open. And from last time, you should have this DTC scaled.stl somewhere. So just double click that and make sure to hit apply. If you don't hit apply, it won't show up. Will that help? DTC scaled hull, if you remember, we had done unzip something last class. So if you don't have that right now, you can just do the unzip again and get it. Any other questions? Okay, so oh yeah, there's a question. No. So the one important thing to remember is this hull, the solid hull.stl file, has nothing to do with the simulated grid. So when we play the grid, you will see things changing in the grid, but nothing will happen to the hull, because this is an independent object that we have imported. So I'll show you how to actually see the hull moving. Okay, so let's remove this DTC hull. and go back to a solid representation, so surface. All right, now the first thing we should look at is what does the water look like, right? This is a block, big block, but there's no flow in here. It's a combination of air on top, water on the bottom. So how do we visualize this? To do that, come here and click this thing called contour. Okay, do not hit apply. We have to change a few settings. Come down here. Oh, if you don't see a lot of settings, you can click this gear box. So if the gear is unselected, you have a fewer options. So select the gear and you will have all the options. Come to contour by and select alpha water. Let's go through the steps and I'll tell you why I'm doing this. So alpha water, come to value range, double click this, put in 0.5. Hit enter and then apply. Okay, so you should get something like this. Is everybody here? So again, let me wait for, well, let me do that again just to make sure everybody's caught up. So let me remove that thing. So everybody should have this open. Just hit the contour button. Come to the value range, change it to 0.5, hit enter, then apply. Then you should have like a flat surface like so. Something is weird here. Let me check. What is weird?
I don't think you clicked alpha.
Oh, sorry. Yeah, that's correct. So I left it as B. So thank you. So you have to select alpha, then apply. Yeah, perfect. So now you see these ridges, that's basically the waves that we put in the simulation. And you see this cutout, that's basically the hull. So visualizing this alpha equals 0.5 gives us the exact interface between air and water. So this is basically the surface of the water waves, okay? And to look at what's happening, we can color this using PRGH is the one that gives us the best visual. So go PRGH, okay? So now you're seeing crests and troughs. If we do it, look at it from the side. No, other side. Oh, come on. Okay, I think so. You see this sinusoidal wave that is being generated in the simulation. And the sinusoidal wave will keep moving downstream and it'll interact with the hull. And you see the water surface breaking when it reaches the hull. So now I told you I'll show you how to show the hull in a nicer way. So do exactly what I do. Open, just load the same foam file again. Okay, I'm loading it twice because it'll allow us to view the hull separately. So hit apply. So I basically loaded the same thing twice, but now come down here, scroll down, and unselect the internal mesh. So all of these names are basically telling you what everything that's shown here. Right now we're looking at the internal mesh. So we don't want the internal mesh, we want the hull. Select that and hit apply. Perfect. So now we have our hull in here. We are only looking at half the, one half of the simulation because It's mirror symmetric. So whatever happens on the left half will happen on the right half. Okay. So, okay, now we have these two different data sets loaded on. Well, it's the same data set, but two different instances. So let me hide the contour for a second and look at this hull and see what happens here. Okay, this hull right now is colored with P. Again, P is useless. So we can color it with PRGH. That's the pressure. You see that? When the wave comes in and hits, there's a high pressure region at the bow. This is basically what we expect to happen, okay? And you can also color this with alpha water. If I color it with alpha water, what will happen? What do you expect to see? Okay, is everybody at this point, or I'll repeat the steps if you want me to. Don't be shy and don't say I'll do it later. Do it now. Okay, anybody have trouble? You tell me now. I know some people might have missed a few steps, so I'll go over it again.
I messed up my Zoom and I'm trying to get it back on screen with the trackpad.
So, okay, wait, you said you messed up your Zoom?
Yeah, so I zoomed in too far and now I can't find it.
Oh, the Zoom here. Okay, so just come to these two buttons and click one of them. Okay, it basically puts everything in view. Yeah, if you zoom too far out or zoom too far in, there's just hit one of these buttons.
Cool, got it.
Okay, anybody else have trouble? Yeah, this program is really, really nice. So anybody else is here with me, have this hull colored?
I don't have
I'm
the
there.
option to select the hull in the internal mesh field. Does that file have to be in the same folder?
Say that once more.
I don't have the option to select the hull. Does that file have to be in the same folder?
No, I think your gear box might not be selected. Let me see if I unselect this. Oh no, that works fine.
I can see the internal mesh and the midplane and all that stuff. I just don't see hull as an option.
So you see a bottom, inlet, midplane, outlet, etc.
Yep.
That's very weird. Yeah, that is unexpected because have you selected the thing called dot foam, or is it selected on contour?
It's on nope, I'm in the AnyName.foam.
Okay, and it doesn't show you the hull. Does anybody else is able to see the hull here?
I can see the hull there.
You can?
I see
Okay.
it.
All right, so weird. I don't know why it doesn't show up for you. Okay. Yeah, no clue. It should show up. But I guess try again and try to load everything again and see if it shows up. So just restart ParaView and see if that helps.
Okay.
Okay. So others who are able to see the hull, now we can color this with alpha water. What will that show us? Well, you can just go ahead and click it and you'll tell me. So this is coloring the hull with the alpha. Alpha is called volume fraction. The red part is where we have 100% water. Blue part is where we have 100% air. And there's a smooth transition in between. So that's our interface. The white line is basically showing us our interface. Okay, let me check. There's a chat. You can see the hull. Okay. Okay, so let's stick with the hull for a second and then we'll go back to contour. So let me hide this. Where is the hide button? Here. Okay. Now, let's put a time counter here. So to do that, we go to filters. Filters or source? Let me see, I don't remember. No, not filters. Source. Source, where is time? No, not source. I keep forgetting this. Temporal. Here. So go to filters, temporal, annotate time filter. Okay, when you click that and hit apply, we will get our time display. Okay, we don't need like 8 decimal points, so you can come down here and change it. Where you see where it says time %F, we just put a 0.2 F, and it makes it 2 decimal points. Okay, so that's a time equals 0.1. We want to see what happens in time. So you just hit play here. You see the play button, hit that, and it will show you frame by frame what happens at 0.1, what happens at 0.2, etc. So let me just hit that play and wait. So you see the water level is changing because there's a wave coming on and going down the hull. Okay, so let me hit the play again and okay, and it's and you might even notice the hull is pitching up and down. Okay, let me line it up. Well, try to line it up with the bottom here, and let's see how the hull moves, if it moves. Okay, let me play it again, and notice if the hull will pitch up and down. So I hope you can see that on your screen. There's a very slight pitch of the nose up and down. That's expected when the wave comes by and hits you. So this simulation you've done is a 6 DOF, 6 degree of freedom simulation. The one we have run here is a very, very rough simulation. This should not be taken to be the truth, okay? To do these simulations properly, you have to do very, very fine grid resolutions and on very large computers. Okay, so anybody was able to play the wave on the hull?
Yes.
I can play it, but I can't. I missed how you got the time to display.
Oh, so for time, you just go to filters. Alphabetical shows you everything, but I'll tell you where exactly it is. So filters, go to temporal, go to annotate time filter. And once you click that, you have to hit apply. Did that work?
Yeah, I got it.
All right, and then hit play, and what do you see?
Yeah, the wave moves and the time counts.
Okay, anybody else able to see that?
Yeah.
Okay, more?
Yes.
Okay, I have 4. All right, anybody else?
Yep.
5. Okay, so seems to work for most people. All right, so that's the wave moving along the hull. Now you can also visualize the pressure on the hull. Let's see, where is it? So remember, you always have to come back to this pipeline browser and select the one that you want to change. Right now it's selected on time filter, so I can't do anything with the time filter. So I have to go back to this hull guy and change from alpha water to pressure rho GH. All right, and now you see how the pressure will vary. So let's play this again. So you see as the wave comes by and hits it, and you'll notice this is what you would expect intuitively. There's a high pressure in the front, which lifts the nose up, And as it passes by, the nose comes back down. Another high pressure, the nose would lift up again. Okay. Now, these colors are very faint, so we can change the color scale. The way you do that is you come here, rescale to custom data range, click that. And you see these are default values that are taken from the data. Let's just change it to, let's say, minus 300 to plus 300 and see what happens. And this usually has to be an iterative process. We'll see what happens and we'll change it again. Okay, maybe too much. So let's change it to minus 500 to plus 500. Okay, all right, fine. Still not beautiful, but okay. So if we play this again, we'll see, okay, high pressure pushes it up, then it comes back down, then there's a high pressure again, it'll push it back up. And you don't have to use this ugly blue and red thing. So if you want to change that, just click this button here.
What is the red smear that goes up the hull? Is that a splash or something?
It might be a splash. Let me see. Yeah, see when the hull bounces back into the water, I think it generates a splash. To see what that is, whether that's a splash, let me activate the contour. Okay, perfect. So you see that's actually the water surface, and that smear corresponds to this basically wave breaking. So let's play it with the water surface and let's see what happens. Now it will be slower because computing the water contour is not easy. So you see, as the wave, as the water face moves across the hull, the pressure changes with it. Again, these look nice, beautiful, but do not take them to be the truth, especially when we are running them on our laptops. Let's see what happens at the back of the hull. So, okay, let me do like an aerial view and see what happens. So there's the initial push up. The hull rises slightly near the nose. We don't see it because we are zoomed out now. And then it goes back down. Okay. Well, maybe to see it, we can make our water slightly transparent. You want to make your contour transparent, select the contour and then toggle advanced properties. And let's come down and find opacity. Okay, there, opacity. Let me decrease it to 0.5. Maybe less, maybe more. Yeah, so our water is basically transparent now. And let me make the water solid color. Okay, and the color, the red color we see is on the hull. Okay, so now we can see what's happening through the transparent water. Let me get rid of the bar here. Okay, and again, you see just with a few rough clicks, we already get a nice visualization. You can make it look beautiful. So intuitively, it makes sense, right? Whenever the hull smashes into the surface, you get a high pressure region. Any questions? Who is here with me? I will count. Just say yes.
Yes.
1,
Yeah.
2, 3,
Yeah.
Yes.
4, 5.
Yes.
Okay, perfect, perfect. So most people are here. That's awesome. It's, yeah. I was imagining we would have a lot of trouble. Okay, cool.
Yeah, this is very cool. This is very cool. Thank you.
Sure. Again, remember, this simulation we have done does not represent reality. It can if you run on a very powerful computer with a lot of grid points. Okay. So that's always a caveat you should keep in mind. Okay, what else was I going to show you? So you know how to visualize the water surface. You know how to look at quantities on the hull. Oh, okay. Now we can, it's weird to look at just half the thing. So we can put a mirror so we see the full thing. So let's do that one by one for the hull and for the contour. So let's do it for the contour first. Just click contour. Then go to filters. And there should be a mirror filter somewhere. Where is mirror? Okay, my screen is too small, so let me search for mirror. Filter, search, mirror. What is it called? Okay, I have to Google what the filter name is. So, para view mirror. Reflection, it's called reflection. Okay, let me see. Okay, so let's search for reflection. Reflect. Yeah, perfect. There's a reflect. So click your contour and hit reflect. Don't hit apply yet. We have to select the axis. So let's see, plane of reflection. What plane should we reflect across? So it seems our mirror plane is the x. X mean? Wait. So x. Yeah, x. This is the x direction that we have the cut along. So let's see. Well, if we make a mistake, we'll fix it. Oh. Okay, wait, I made a mistake. So y, z plane. Let me just try all of them and see what happens. Oh, okay, y. So the reflect plane just means the direction you want to reflect in. And you see here, it shows us that's the y direction. So now we have the water plane visualized in the whole domain. There's no color right now, so let's color it with PRGH. All right, and then we see our wave coming in. Let's do the same for the hull. So let's select our hull. Where is the hull? Okay, this is the hull guy, right? Yeah, that's the hull. So filter, search, reflect. And plane is the Y plane, apply. Perfect. So we have our hull. Okay, and again, you can decrease the opacity of the water plane. So reflect is the water plane, and you can rename it. We can rename it. Does it allow us to? Doesn't allow us to rename. Fine, don't care. So select reflect. Make sure this gearbox is selected, and go to opacity. Opacity is where. Here, opacity. Okay, let's drop it. Oh, too much. Okay, fine. Yeah, now we see our water plane is transparent. All right, and again, we can change since the pressure values look too faint, we can change the color scale. So select reflect again. That's our water plane. Come on, all right. And then go to rescale. So -500, okay, let's see. I didn't do anything. Oh, let me try minus 300 to 300. Okay, fine. All right. So, and the last time I told you how you can change the properties of this wave. So the wave, we specified it to be a certain wavelength, a certain height, and a certain direction. And you can change all of that in the text files we were editing before we ran the simulation. So you see the wave comes in and then breaks over here. Okay. So next question you have, well, before I tell you what question you have, do you have any questions for me? No questions? Okay, let's, I don't like this text is too large. So let me make it smaller by selecting it and then going to, what is its property? Ah, it's 18, let me change it to 12. Yeah, 12 is fine. Okay, and then the next question you should have for me is, how can I make an animation out of this? Go to File and hit Save Animation. Okay, so let's save in Downloads again. And you can select different options. So when we do real production things, we output images for each frame. So I usually do PNG and then use any software to combine everything together. That is both good, better for quality, and it allows me to change the frame rate if I want. Right now, you can just select the AVI file, or if you have MP4, you can select MP4. And we can say how test. Hit enter. Fine. Okay, then give it a few minutes. Not a few minutes, just a few seconds. It's basically playing it frame by frame and writing all the frames into one video file. Oh, I didn't tell you how to change the red-blue color scale, not the color scheme. So remind me to do that after. So let's go to downloads. What did we save? We saved hulltest.avi. Let's play it. So it's playing at 1 frame per second. Before we save, we could have selected how many frames per second we want. Okay, so right. If you don't like the red and blue, well, let me make our hull a different color. So where is the hull? Reflect to. Okay, let me make it a solid color. Let me make it, what do you want? Pink? No, pink. I'm trying to get it to not clash with the color we have here. So purple. Fine, it can stay purple. Okay, and if you want to change the color scheme of your waves, let's select the waves. Where is the waves? Waves are here. And then you can do many, many different things with the color. Just go to edit color map. And here, come to choose presets, the one with the heart. You can select anything you want. Just select one and hit apply. It'll change the color map. Black, blue, white, let's see. Okay, so you can basically do anything you want. It's a very nice program. Okay, any questions? Anybody miss any steps? Don't hesitate. Tell me now, because if you missed it, there are 3 other people who missed it.
Can you do something completely under the surface, like a submarine?
Completely submerged simulation is much easier to do than this thing I've showed you. Because creating such a surface is very, very difficult to do in simulations. So yeah, you can do a completely submerged thing. Instead of copying the example that we used, so we copied DTC hull away from the foam tutorials. You copy something else. If just ask Google what's a good case to copy and start with. If you have too much trouble, come and ask me. More
Thanks.
questions? Anything else? Okay, so one more thing I want to show you is we see the hull moving up and down. How does that happen in the simulation? You don't have to follow along. I'll just show you. So just go to foam, and I need to be able to visualize the midplane. And then I'll highlight it. Okay, so if the eye is not visible, it won't be visible. So we have the midplane, basically the cut. And let me change the midplane to wireframe. Okay. And let me hide the solid hull. So you see this, let me also disable the internal mesh. It'll break a few things, but I don't care. I just care about the midplane. So you see, that's all the cells you see are where the fluid flow is simulated. Everything that's blank is solid. So there's nothing, no simulation happening in the solid region. And the nice thing about the program is the mesh changes. That's what allows the hull to move up and down. So pay close attention to what happens to the mesh as I play it. So you see the whole mesh is deforming to allow for the 6 degree of freedom motion. Again, these are very, very advanced techniques, and we are very fortunate that the open foam people have implemented all of this already. Doing this on your own would take, let's say, 10 years from scratch. All right, okay, so any questions? So you know how to do a simulation. Now you will need to use these tools for your project. If you haven't looked at the project, it's basically very open-ended. You pick any design, not your senior design project, but you pick any ship-related design problem that you want to solve. Let's say you want to create a crazy catamaran or a crazy, like a lifting airfoil hull. You make that design and you look at what the flow looks like around it. Okay. Questions about that? It's a group project. You should work in groups of 3. Mixing of undergrads and grads is fine. Are you still here? I don't know if you're okay.
Yeah.
All right. So any questions about that? And
Couple questions.
Yeah.
How are we going to get into groups? Just voluntarily form groups, or?
Yeah, you decide your own group members. 3 people, no less, no more. We have exactly 21 people. So we will have 7 groups. So just reach out to others and see who might need a member, a team member.
Okay, one other question. If you were to do something with a like an aerodynamic hull or something that had aerostatic lift or whatever, this can't do anything with that, right?
So here you have both air and water. That's why we have the interface. So it might work. You can do it, of course, but you might have to change a few things, and it becomes more difficult. But a hydrofoil should work fine. I mean, look at this. We had our bulbous, where is it? We had our bulbous nose here, right? And that affects the flow, that affects the pressure distribution. So anything that's fully submerged, if you have a nice airfoil, it should generate upward lift. If you create a planing hull, you should get the planing effects. That's why this 6 degree of freedom option is very nice. And remember, for the projects, you have to do all the stability analysis and the resistance calculations that we will talk about theoretically. And this should be like the wrapping up and the final, what is it called, bow? You tie up the bow on the project and you're done. So don't forget like all the stuff we have learned in class. You need to use all of that.
When is the project due?
I haven't set a due date yet. I'll set it towards the end of your, when is your senior design due? Can anybody check right now? Okay, if I say anybody, nobody will check. Who asked the question?
Brennan.
All right, Brennan, can you please check when the senior design is due? When you have the FDR? So, I mean, you will have at least 1 month, so get started early. You have to come up with the design, you have to do all the analysis, you have to run the simulation. So don't leave it for the last minute. Okay, Brendan, just let us know whenever you find it. Let's see, there was something else I forgot.
What software should we use to develop our STL files?
Any CAD model can be converted into an STL file, so it doesn't matter. You pick whichever software you like doing CAD with. If you have trouble converting the CAD to STL, well, I mean, just ask Google. There's many free options. There's one called FreeCAD.
We have our FDR presentation on April 15th.
April 15th, okay. So that'll be basically, you'll be done with senior design, correct? Or you have to revise your report?
Yeah, so the draft is due on the 9th. The FDR presentation is the 15th, and then the revised report is due the 19th.
All right. So, and when is our exam? The exam date I don't set. It's set by the university, so I have to check. Exam is April 28th. Okay, so 19th, 28th. Revision. Okay, 19th, 28th.
You're in March right now.
Oh, sorry. 28th. Okay, 19th. Okay.
You're in May right now.
Wait,
no, never mind.
Yeah. All right. 19. How about we? How about we set it for April 23? Any objections? All right, perfect. So that's your due date, April 23rd. I will update the due date on Canvas. All right, perfect. So anything else?
How long would it take you to create this simulation from scratch?
You mean write a software that does this?
I don't know. You said it would take like one of us 10 years. I was just wondering how long it would take you.
Oh, how long it would take me? It would take me like maybe 2.5 years. Maybe 2 years, yeah.
Okay.
So yeah, that's not easy to do. This is, yeah, even I cannot do it quickly. So again, we are very, very fortunate that these people have made this software and made it freely available for everybody to use. And they keep improving it, they keep developing it. So OpenFOAM is very, very nice. Put it on your resume once you learn how to use it well. Because yeah, people know OpenFOAM. Okay, anything else? Okay, so try to do this with a different hull, not just this guy. You just have to replace, well, try it and ask me if you have trouble. If many people have trouble, I'll show you what to do. And again, Google is your friend, so ask Google. All right, let's go back to paper and pen.
One more question. Is the same time settings fine for the project?
You mean how frequent you save data?
Yeah, like all this, the simulation time length and the time period.
No, that's we did that because we just wanted a quick result. So it's 1 second of simulation, which is not nice. So run longer, like 10 seconds or 20 seconds.
Okay.
Saving interval, it just, you know, if you save more files, it'll take a more disk space, but you will get a nicer video because you have more frames. Ideally, you want to save like 30 frames every 1 second, but we save 10 frames 1 second.
Okay, sounds good.
Yeah, but the simulation itself, the time steps it takes is much smaller. It's on the order of, what is it? Let me check. We see it in here. So DTC, oh, you don't see my screen. So if you just go to the DTC Hull Wave, go to System, Control Dictionary, the delta T is the simulation time. So the simulation is proceeding 0.0001 seconds every step it takes. But it doesn't save data every step it takes. It saves data when you specify it, the right interval. So don't change this delta T. You make it smaller, your simulation, or you make it larger, your simulation will run faster, but it will become less accurate. You make it too small, your simulation will never finish. Okay. Okay, anything else? All right, so I want to do one trim example which you can use in your homework. Again, if your aggregate grade point at this time is less than 50%, please ask me for help if you need it. If you're above 50%, it's fine. Try to push it as high as possible. Okay, so, all right. So we started talking about trim, all right? All of the early parts of the class, we've talked about roll, and now we're talking about trim, okay? And we said, all right, trimming happens about the LCF, and we can have different draft values at the fore and the aft. And we were just starting to talk about how the trim angle, theta, is related to the two. Okay. The fore fore draft minus aft draft is what we call trim length. Okay? And the trim angle is just defined T over L. And we said whoever is riding lower into the water, if the 4 is riding lower into the water, we call it trimmed by the, wait, I always have to think this carefully. So, all right, I think I have it. Who is riding lower in the water? Nose up or nose down in the first case? Think about this. Aft.
Nose up.
Yeah, it's nose up. The aft is submerged more than the 4, so it's basically nose up. And whoever's riding lower into the water, we call it trimmed by that part, trimmed by the stern, because our stern is riding lower. In this case, we have nose down, trimmed by the bow, because the bow is riding lower in the water. Okay. So we will talk about stability in trim very briefly, because again, that's not a big issue compared to stability in roll. So stability, so as we all remember, when we talk about roll, Ix is the moment of inertia we care about. When we talk about pitch, we talk about the Iy, the transverse axis. And since we are pitching about the LCF, we have to have this axis pass through the LCF. Okay, and similar to before, we have Km longitudinal equal AB plus BM longitudinal. Every time we've talked about roll, we've talked about Km transverse. Now we are talking about Km longitudinal. So this is longitudinal. And this becomes KB plus I longitudinal over nabla. This part is same as before. It's the submerged volume. And this guy is so you can already see that when we roll about this, moment of inertia is not as large as when we do this. Okay, so now this value will be much, much larger for this type of motion, or the pitching motion. So this is much larger compared to roll stability. All right. So you will almost never be asked to compute the GM longitudinal because we know it will come out to be greater than 0. But what you will be asked to do is figure out if you load cargo a certain way, is your nose pointing to the sky or is it pointing to the depths? So that is something we will learn how to do. So we can compute what moment is required to trim the ship by 1 meter. 1 meter is a huge amount of trim. Think about this. The draft of your aft is 1 meter different from the draft of the fore, either up or down. So that's a huge number. Okay. So this moment, we call it MCT. Just means moment required to change trim, MCT, by 1 meter. And for this could be part of the graphs we were talking about, the hydrostatic curves. So if you know the value of MCT, you can figure out very quickly, if you move cargo from one place to another, what is the resulting change in trim. So to figure out all of this, let's change the trim by moving a weight W from its initial location to a new location. H meters forward. Okay, let me draw a sketch. Let's say our weight was here at G0, and we move it over there. And our water line used to be nice and horizontal, but now it is at an angle theta, trim angle theta. All right. So when we do this, what's going to happen? When we take something off from the aft and move it forward, what is going to happen? Think in terms of center of gravity. What's going to happen to the center of gravity? All right, stop playing with your computers and come to paper and pen. So moving this guy from here to there, what's going to happen to center of gravity? Will it move up, down, left, right?
It'll move forwards.
Okay, And will it move up or down?
It'll diminish the angle, move down, move the bow down.
Yeah, so it'll basically change the angle of the hull, but so if we are here at G0, you said it'll move forward. Will it move up or down?
It'll stay the same.
Stay the same because we didn't add any mass, we didn't subtract any mass. We just shifted it. So G0 will go to somewhere, G1. We don't know where yet. But we know how to compute this. We know when we shift things, we know how to compute the resulting new combined CG. So we just say, so we know G1 will be G0, delta 0, okay? We removed mass from this position, so we put a minus W times little G0. We added mass at the forward position, so we put a plus W times G1 divided by initial mass, mass subtracted, mass added. And I'm using weights, but you can change it to mass just by dividing by acceleration due to gravity. So, and we know here where delta 0 is combined delta ship plus W, because the W weight was already on board. We didn't add it. Okay, so that's our simple center of mass formula. So when we rearrange this, we get the shift G0 to G1 is basically G1 minus G0. When we rearrange this, we get, what do we get? G1 minus G0 W over delta 0, which is G0 G1 W over delta 0, which is basically H times W over delta 0. Okay, so that's our shift in the combined center of gravity. When that shift happens, we look at what happens to our the meta center. So let's say this was our G0, this was our meta center location. And now G0 has moved to G1, causing a tilt trim theta. Okay, just using trigonometry, you see here tan theta is G0 G1 over M G0 M. Okay, G0 G1 we just found here, we'll just plug that in. So we have W times H divided by okay. So we have a way to relate the change in angle to the weight and how far it moved. And since we are out of time, we'll finish this and do the examples next class. Any questions? Okay, see you on Friday.